Hi, this is Karen Singmaster, and this is the recorded seminar for experiment 2, which is called the hydrate. In this experiment, what you will be doing is you will be taking a hydrated salt. This is the salt here, and this is the water, which is why it's called the hydrate, and cooking it with a Bunsen burner, heating it up, and that will drive away the water. The water will leave as a gas, and then it will leave just the solid. Now, please be aware, this is not the salt you'll be using. This is an example. The formula for the salt you'll be using will be given to you in the lab report and in the experiment. So the goal for the experiment is to find the value of X. When that salt has the water attached to it, it's called a hydrate salt. When that salt has no water attached to it, it's called the anhydrous salt, or sometimes in the lab manual we'll call anhydrous residue. Also remember, this is a balanced chemical reaction. Balanced chemical reactions are based on either number of particles. So this is 1 molecule of cobalt-2 nitrate for every X number of water molecules, or it's based on moles, 1 mole of cobalt-2 nitrate for every X number of moles of water. But when you look at this in terms of particles, in terms of molecules, if you have 1 hydrate salt molecule, meaning the cobalt-2 nitrate hydride, or hydrate, excuse me, not hydride, hydrate, that X value has to be a whole number, right? Because you can't have part of a water molecule. Either you have a water molecule, a whole water molecule, or you do not. All right. The other thing to remember is this is not mass, right? The relationship here is not 1 gram of the hydrate salt gives you 1 gram of anhydrous salt and 1 gram of water, or X grams of water. This is not a mass relationship. So even though we weigh things with a balance and we get masses, when you're doing calculations for chemical reactions like this, like trying to find X, you're going to have to convert those masses to number of moles, or if you want to do it, to number of particles. So again, our experiment is going to be to warm up a hydrate warm enough to drive away the water. We are going to weigh the hydrate. We're going to weigh the anhydrous salt, because clearly we can't weigh the water. The water's gone away as a gas, but we know that mass has to be conserved. So whatever mass we have of hydrate salt has to be equivalent to the sum of these two masses, right? So the goal of the experiment is to find the percent water, just so we practice percent water, and that's a mass-based percent. And then we want to find the number of molecules of water associated with the hydrate salt. So we're trying to find X. I remind you that the percent water is, in the hydrate, would be the mass of the water divided over the mass of the whole. So it would be the mass of the whole hydrate. So in this experiment, you'll be using the balance a lot. You'll be using a Bunsen burner, okay? You'll be using a crucible, etc. So you'll have some new things to try out. So let's roll this down a little bit. All right, so the learning objectives for this experiment are that you're going to be reviewing from high school chemistry how to convert mass to moles to number of particles. If you remember how to do that, there you're in good shape. Avogadro's number and using molecular weights to do it. We use molecular weights and molecular mass interchangeably, but in a physics course, they'll tell you that there is a difference. We're going to calculate the percent weight and use it to find empirical formulas. That's technically what you're doing here. You're finding a formula. Excuse me, here, you're finding the formula, right? And that can be done backwards, but we're not going to do that backwards as an experiment. Rather, that would be some practice problems of you're giving an empirical formula and you can backtrack and figure out percent weight. So you can give it a molecular formula and you can backtrack and figure out weights. You're also going to learn how to use a Bunsen burner, a crucible, right? And again, you're using the balance. The analytical balance again, all right? Analytical balance again. All right, so as you see, I correct these as I go. Your experimental setup, you're gonna have a ring stand and a Bunsen burner, and there'll be a video on how to use the Bunsen burner. There'll be a crucible and a cover. And that's what a crucible and cover look like. And so you can use your triangle. There's a wire triangle in the box, or in my case, I ended up using a wire mesh just because it was just easier for me to remove the crucible and cover quicker than trying to dig it out of that triangle that is there. And again, because I'm videoing the experiments for all of you and trying to do this as quickly as possible, I've got to be a little more efficient, okay? The experimental procedure is fairly straightforward. We have to find, clearly we have to know, I'm coming back up here, how much hydrate we put in there. So we're going to have to weigh it. And clearly we're weighing it in something. In this case, we're weighing it inside the crucible. So we better know what the crucible weighs before we put the hydrate in there. And then after heating it, we're going to have to weigh it again. So it seems fairly straightforward, but there's some additional things that need to be considered. First, after setting up your equipment sort of like this, you need to realize that that crucible could be dirty from the past, right? So you can rinse it with water and all that, but then it's going to be wet. And so however way you do it, whether you rinse it and with water and soap and remove the water, or you try to just burn off whatever's in there that could burn off and mess up your experiment, you're going to have to warm up the crucible to a really high temperature to make sure that any residues or anything are gone. You don't want that to be weighed as part of the hydrate. So the first thing you're going to do is you set up your equipment, you heat up the crucible and cover to clean it up before weighing, all right? Then you're going to cool it, because you can't weigh things when they're hot or cold. They weigh poorly. When they're cold, they start to condense air, and so the weight keeps creeping up. When they're hot, there's convection currents that start making the crucible weight to be lower. And so you have to make sure that the item you're weighing is at room temperature the same way as the analytical balance is at room temperature. So you let the crucible cool. That can be 5-10 minutes, and you do heat up, you do cook it with the cover, because you do need the cover during the experiment. So you then go weigh the crucible and cover once cooled, and then you start adding hydrate so that you have between 0.9 and 1.1 grams, and you weigh it again. And clearly the difference between these two values would give you the weight of the hydrate. So that's where you're getting that first value for the weight of the hydrate. You now get to heat the hydrate in the same experimental setup. You do want to start heating it slowly. You want to fan the flame to warm it up slowly. The reason for this is that this crystal structure has trapped water in it. And so if you heat it up too quickly, you might have an effect that's called the popcorn effect, which is that the whole thing starts to fly out. And so you heat it up slowly, say over 4 or 5 minutes, and then you crank it up to heat it as hot as possible. All right. And we'll show you in the video for how to set up a Bunsen burner, how to get it to the place where it's going to heat up that crucible as hot as possible. I was going to say something else here. Let me remind myself here. Remember, it's about 15 minutes of this, so that you want to heat the hydrate all together, just to make sure you drive the water out. Okay, you don't drive the water out, then you don't do the reaction to completion. Again, now that you've heated up the hydrate, you got to cool the crucible. You're going to let it cool down and then weigh it. This is the weight for the first time, for the first heating period, after the first heating period. This weight would correspond, in theory, to just the weight of the anhydrous material. And I'll go back up again, right? If you drove out all the water, it left us a gas, and this is what's left. And so technically, what's left in there is just the anhydrous salt, right? So you weigh it. And now the question is, well, did you drive all the water out? I mean, you think you did the experiment great, but maybe you want to confirm it just in case, right? So you heat the crucible again now, but you don't have to be so cautious, and get it red hot again for 5 minutes, and then cool it down and weigh it for a second time. If you drove all the water away the first time, then these two weights should be the same. If you didn't, then this extra heating hopefully helped you drive the water that you didn't get out the first time, and this should be your best weight because it's the one where it's driven the most water because you've heated it twice. But again, if you've done this experiment well, then both of those values would be very similar. All right. So what data are you collecting? You're collecting the weight of the crucible and the empty with the cover, right? And then you're adding the hydrate. So you expect this number to be larger than that one, right? And then you're going to cook the crucible with the hydrate in it, right? Warm up the hydrate so the water goes away. So then what you're left with is the anhydrous salt. And you're going to do this twice. And again, as we stated, if you're really good at driving away the water the first time, then these two numbers should be the same. If on the other hand, you were a little bit too cautious warming it up because you were scared or you were worried about the popcorn effect, then the second time when you're blasting at it super hot, then this weight would be even a little lower because you lost a little more water and you would use the second heating as your value. So typically we only have time in lab to do 2 of these experiments, right? You do the run twice with the same hydrate so that you can compare and see if you got it, if you did well, the 2 experimental runs. The reason we can't do too many is because of all the time spent heating and cooling and weighing and all that. Typically we have 24 students in lab, so there might be a line out of balance and things like that. For the online experiment, what we're going to do is just video 1 run. And you're going to watch those videos and collect the data to write in your report sheet from those videos for run 1. Then the report sheet will have 2 more runs, the data for 2 other runs there. There's no need for us to video the other 2 runs and have you waiting, watching the heating and all that. So we've given you now 2 experimental runs in addition to the 1 you see in the video. Some experimental issues to keep in mind. Again, we talked about this already. You can't weigh hot or cold items, so you have to wait for the crucible to cool. And there are sources of error. I mean, you can make mistakes. If you spill the hydrate after weighing it, then you need to start over. If you don't heat long enough or hot enough, then all the water isn't driven away. That's why we do that second heating. And then if you're not careful, if you go full blast heating from the get-go, the material can act like popcorn and spray out. And so then you lose material and that damages your run. It makes the calculations be wrong. You could also spill some of the anhydrous salt. Maybe you tilt, by mistake, you flip over the crucible. And then again, you would end up having to start over, okay? So those are some of the things that the mistakes students make when doing this experiment. Unfortunately, you don't get to be in lab to make the mistakes, so we have to sort of warn you about what mistakes are possible. So let's walk through some sample calculations here. And again, we're using the cobalt-2 nitrate, but that's not your salt. It's a different salt. So don't be mimicking these molecular weights here or for the cobalt nitrate, because it will be wrong. You have to calculate molecular weight for your salt. All right. So here's what you have. You're going to have the weight of the crucible and cover, the weight of the crucible, cover, and hydrate. And then you're going to have the weight, crucible, and cover, and anhydrous salt. Now up here, you had 4 data, right? But we said, hey, that second heating, if you did it well, should match the first. And if you didn't do the experiment well, then this is the better run. And so you would use that second value, right? So that's why we only have 3 values here. And again, notice the crucible and cover is the same for all of them, right? So these 2 have additional material in there, so they should be heavier than the crucible and the cover, right? Okay, so look that over carefully so that you're aware of that. How much they should differ by, we don't know, but we understand that when we add hydrate to a crucible and cover, then the weight should have gone up. Okay, and I'm just correcting things as I see them. So what are your first calculations here? So if you remember, we wanted, and again, I scroll up, the percent water. Right? So the percent water is the weight of the water divided by the weight of the hydrate. Okay? So I go to my calculations here, and I can see that if I take this top value and subtract it from the second value, the crucible and cover go away, and I'm just left with the hydrate. So there's the weight of the hydrate for my equation. So the weight of the hydrate would be 26.4300 minus 24.2350. Now, why did I use these numbers? I use these numbers to remind you of significant digits, okay? This guy is good to 4 decimal places. This guy is good to 4 decimal places. When adding and subtracting, you keep the same number of decimal places as the guy with the least. Since they're both good to 4 decimal places, that's zeros written there. This number is good to 5 significant digits, okay? And that is important because you have really pretty good data here, right? All right, you can go find in the same way the weight of the anhydrous residue. Right, we see the crucible and cover in blue, crucible and cover. So if I subtract this top value from this bottom value, what's left is the anhydrous salt. So I do that again, and again I watch my sig figs. This is good to 4 decimal places, this is good to 4 decimal places, so my answer is good to 4 decimal places, because when adding and subtracting, it's the number of decimal places that matter, okay? So the difference between these two is the water, right? Let's go back up. So if I have the mass of this and the mass of this, the only thing left is the water. And so, and remember, mass has to be conserved. Whatever started out with has to add up to whatever I ended up with. So I come back down here, and for the weight of the water, I can either subtract one of this one from that one, or I could in theory subtract this value from that value, because the difference between these two is going to be the water. So there's the weight of the water. The equation was, and oh, just so you realize, when you subtract these two values, the number's less than 1. And so again, you're good to 4 decimal places, so your answer is good to 4 decimal places, but this number that now only has 4 significant digits, okay? So your percent water in the hydrate was the mass of the water, so I got that there, divided by the mass of the hydrate, so I have that there, and then times 100% to make it a pretty number. Now, since we're multiplying and dividing here, when you multiply and divide, you keep the number of sig figs of the guy with the least sig figs. Now the 100% has infinite number of sig figs. I could have written 100.0000, right? And so the guy with the least digits here is the mass of the water with 4. So that's why my answer only has 4 significant digits. So that's how I find the percent water. The second part of the experiment was to calculate the value of X in the formula. Now again, I remind you of this. We mentioned it when we started this discussion. The balanced reactions are based on the number of moles or number of molecules, not based on mass. So right now here we have mass of the hydrate, mass of the anhydrous residue, mass of the water. But we can't use that to figure out X, because X is a measure of the number of moles of water for every mole of the hydrate. So we have to change the relevant units here to units of mass, to units of moles, okay? So we're trying to figure out for every one of these, remember there's one hydrate for every one anhydrous residue. So for every one of these, how many waters do I have, right? We also know that X has to be a whole number, because as we mentioned before, you can't have half a molecule of water. So again, we're going to convert these materials to moles using molecular weights. Now, I can't use the hydrate, right? I don't know the molecular weight of the hydrate, and I come back up here again. I can't find the molecular weight of the hydrate because I don't know X. But this formula here, I can calculate its molecular weight. This formula here, I can calculate its molecular weight, and I can see the ratio between those two moles. If I divide the moles of water by the 1 associated with the 1 mole of cobalt nitrate here, I would get X. So if I can figure out the moles of water and divide it by the moles of the anhydrous salt, I should get X. So it's the value of the anhydrous salt that's going to be useful for my finding X. Okay, so I've got to use my molecular weights, and I'm not going to remind you how to do molecular weights here. That should be remembered from high school chemistry or from your lectures. So again, I write the numbers here. There's the mass of water, and this is the mass of, let's clean this up so that the units all work out. Control V. Okay, there's the mass of cobalt nitrate from above. So the same numbers we had up here are there. Okay, and then I have to convert it to moles, and start out with mass. And so the way to convert it to moles is to know the equivalency, the relationship between 1 mole of water and a set number of grams of water. So 1 mole of water weighs 18 grams. I have to do this calculation to at least 4 sig figs. My data is good to 4 sig figs. And so in that respect, I'm going to have to figure this out to 4 sig figs. So I'm looking at this here, right? And the units cancel out, the grams of water and the grams of water and the 1 mole of H2O. And so I have the mole of water, and I have 4 sig figs and 4 sig figs, so my answer gets 4 sig figs. Now notice I have a mistake here, and I'll point it out in a second. The mass of cobalt nitrate, cobalt 2 nitrate, has 5 sig figs. So if I'm going to be using that same mass here, I need to have this molecular weight to 5 sig figs. So I'm going to add a 0 there, right? At this moment in time, I don't know what the actual value is. I can correct it later. It's not a big deal, because in the end, X is going to be a whole number, right? So my X is 1, 2, 3, 4, 5. I don't need 5 significant digits. I'm going to get a value, and that value is going to be better be, if I've done the experiment correctly without any accidents or anything, better be relatively close to a whole number. And so because of that, I feel comfortable writing a 0 there. Even if it were a 2, it's not going to be a big deal. I do my calculation, and I only wrote it out to 4 sig figs. I should write it to 5 sig figs. So I'm going to go 1.38 divided by 182.9, or 1. So I wrote a 1 there, okay? And sometimes the mistakes are intentional, and other times they aren't. So because when I see the mistake, then I force myself to talk about it. And so then that makes you see how my reasoning is going on here. Okay, so I have my moles of water, I have my moles of cobalt nitrate, cobalt 2 nitrate, the anhydrous salt. And now I want to remind you that for your lab, you got to find that molecular weight, okay? Because it's not cobalt nitrate what you're using for the experiment. It'll be in the report sheet and in the lab description. Okay, so now I have to figure out what X is. So I know there's 1 or more molecules of water. So if I divide by how many moles of water I have, moles of cobalt nitrate I have, that the moles of water, I should get a whole number. So what it's telling me is all I have to do is find the ratio of the moles of water to anhydrous salt, and that better be a whole number. And so I got 0.04528. I'm dividing it by 0.5, and I'll put the 1 there, but realize it's not relevant, right? Because in the end, 4 digits divided by 5 digits is going to give me 4 digits. 0.04528 divided by 0.0075451 equals 6.001. Okay, and this is moles of water for every 1 mole of CONO3 2. Okay, so that is my X. I subscript and subscripted here, so I do this right. So this is my X, right? Okay, so that's telling me that the formula is cobalt 2 nitrate hexahydrate, hexa for 6. So there's 6 water molecules for every cobalt nitrate. And realize again, I mean, the 4 significant digits, I have something that's less different than 6, but we know X has to be a whole number, so it's 6, right? Okay, so let's go back a minute here. because now we know how the calculations are done. And so let's look at a problem or two here. If you made some mistake here, what effect it would have. So say, for example, you don't heat it long enough or you don't get it hot enough, right? If you do that, then this anhydrous salt will still have some water in it, right? So your amount of water will be less. Your amount of water would be a smaller number here, which means your percent water would be smaller if you don't heat it well enough, right? Because you didn't drive out all the water. The popcorn effect is a little different, or spilling the anhydrous salt before weighing it, right? Because anything that after you start the experiment and you're heating the hydrate, you've got your hydrate value here correctly figured out, right? He's good because you didn't make a mistake before then. But your mistake occurs once you're heating the hydrate. You get the popcorn effect, stuff flies out, you spill some of it before you weigh it. If you spill it, this number will be smaller. Anything that leaves the crucible in between you heating the hydrate and you heating the anhydrous salt is going to be assumed to be water, because that's the only thing that should leave the crucible. So when you do your calculations, your mass of water will be much larger, and so then your percent water will be incorrect, okay? And then in addition, you'll end up with an X value that's greater than the actual value, right? Because you started out with a larger amount of water here. Okay, all right, that takes care of this experiment. Remember to attend your lab next week. The report sheet, we'll write it here. Report sheet is due at the end of lab. So the experiment is going to go relatively quickly because I'm not standing in line to weigh the hydrate and all that. I'm not sitting there making you watch me heat it for 15 minutes and watching me cool it for 10 minutes. I had to do all that and it took time, but obviously it makes no sense to record that for you to just sit there watching a crucible cool. So that means that the experiment, you can get, the whole discussion of the experiment with your lab instructor, watching the videos and getting your report sheet to have the data for that first run should take under an hour. That gives you ample time in lab to complete the report sheet. So during your lab period, you complete the report sheet and you submit it. It gives you also the opportunity to discuss with your lab instructor what's going on. In addition, we might add in a problem or two or a worksheet to be done during that extra time period so that you spend, some time in the lab. It might not be exactly 3 hours, but, it should be at, you'll end up spending an hour and a half to 2 hours in lab. Realize that typically when we do this experiment in lab, it is a full lab period because of all the weighing and all the heating and all the cooling and all that. All right. All right. Thank you so much. And I'll see you next time. Stay safe and healthy. Bye.